So if anyone can't make it to the webinar, then at least they'll be able to watch the recording. Okay, Andy, I think probably we should start now. What do you think?
I think so, Ron, yes.
Okay. All right, welcome everyone. We've got about an hour to spend here today, and the plan is to talk about asset integrity. Now, there are three of us on the call here, and all of us are available for you. My name is Ron Friend. I work with the Competency Alliance. You may well know it from the name PetroSkills, and PetroSkills is part of the Competency Alliance. I'm VP with special responsibility for net zero renewables right now, but for my sins, I'm also the discipline manager for mechanical engineering. So I do have quite a bit of background with this. In my working life, I've been a mechanical engineer all my life. I've done a lot of work on looking after static plant, so pressure vessels, piping, tanks, and so on, and running inspection programs and repairs. So what we're trying to do today is to talk about the basic issues behind integrity problems that we're going to face with non-rotating equipment. Now, I'm just going to ask my two colleagues to introduce themselves. So Andy, could you introduce yourself?
Yeah, thank you, Ron. Hi, everyone, and welcome to this webinar. I'd just like to mention we're running this webinar together with the University of Doha for Science and Technology, our local partner in Qatar. So I'm Andy Gibbons. I'm a chemical engineer by background. I worked for many years with Shell and with Nova Chemicals and with other organizations, mostly in operational roles. So I was a shift manager, operations manager, ultimately a site manager. I've been in technical roles as well. And within PetroSkills, the Competency Alliance, I teach a number of the process safety management and process safety engineering courses. Conrad?
Thank you, Andy. Yeah, my name is Conrad Jovan. I'm based also in the Middle East, currently located in Muscat, Oman, and I support Andy and the team with process safety management training within the region. Also, I deliver simulation training, and my background is mechanical maintenance initially, then I went into operations, and for some unknown reason, I must have had a bang to the head. I studied human resource management and development for my master's. However, that has helped in some strange kind of way. Thank you so much. It's a pleasure to be here.
Thanks, Conrad. Just a couple of points. As we're going through the webinar, you'll have an opportunity to ask any questions if you go into chat. And Conrad is going to be monitoring the chat. So if you've got any questions, Conrad will stop me at the appropriate time and we'll address them. At the end of the session, we will have time for Q&A. So if you want to leave your question until the end, you're fine. Otherwise, jump into chat and you're welcome. Okay, all right, let's get going. Right, the plan is to talk about asset integrity. And when we do talk about asset integrity, we're talking about primarily loss of containment and the dangers associated with that loss of containment. So what I'm going to try and address here is, first of all, why do we have loss of containment, particularly in oil and gas plants? Now, if you do have a loss of containment, you need to figure out why. What's caused that loss of containment, or what could potentially cause a loss of containment? And once you know why it's happening, you can then decide on an appropriate inspection technology to identify the problem before it becomes a loss of containment. And once we understand the appropriate technologies for inspection, we're then going to develop an asset integrity program. And I use the word effective because there are quite a few asset integrity programs I've seen that are not particularly effective. So the first question, What can we do to ensure optimal integrity of our static plant? Okay, that's a very big question, and we'll jump into it pretty quickly. Well, just one thing, ladies and gentlemen, if you have your cell phones beside you, we will be asking some questions, and we'll be asking you to contribute somewhat. So just make sure you got your cell phones ready, but not yet, because first of all, I'm going, well, actually, yes, we are. Here it is. I'm going to ask you, use one word to describe what integrity means to you. Now, if you scan that QR code, that will get you into Slido. So if you could jump onto that. And what I'm trying to figure out is what does integrity mean to you? Because if I get 10 people in a room, I often get 10 different answers. Okay, robust, safety, inspection, fit for safety, fit for service. That word safe is coming up time and again. We've got sealing, yeah, quality, quality assurance, stability, life, meeting standards. Now that's a very important part. Containment, operational, produce safely, ensure all asset and inspection good and protective. Trust, oh, I like that word, trust. Reliable. Oh, nice. This is what I would like. This is what I like to see. Andy, I don't know if you can take a screenshot of this, but I would like to keep this and maybe let people see what we're actually doing here. Okay, so what we've got is when we're using the word integrity, all of the things that I see on my screen are true. And if we have a piece of equipment and I want to maintain the integrity of that piece of equipment, I do want continued safety. I need to trust my equipment. My equipment needs to be reliable. And the things I do to achieve that integrity, all those different things. I've got quality assurance. I've got my inspections. I need containment and so on. But let's have a look to see what API says. Thank you for contributing there, guys. It does help. The API definition of integrity. The ability of an asset, such as pipelines, refineries, or storage tanks, to operate safely, reliably, and efficiently. See those two words there? Safely, reliably. And those were the two big hits that we got in that word cloud. So to operate safely, reliably, and efficiently while maintaining compliance with regulatory and industry standards. Now, there's a little note there that says it involves the prevention of failures, leaks, and accidents that could compromise safety, the environment, or operational performance. So what we're saying is we have to look after our equipment to make sure it's reliable and we're operating it safely. And that's the key. I'm going to jump on here and I'm going to hand this over to you now, Andy. If you could take us through this.
Thanks, Ron. We have a number of different frameworks that we can use to set up our process safety management system. And one of the most common frameworks is the risk-based process safety framework coming from the Center for Chemical Process Safety. And within that framework, there are 4 pillars. The first one is we need to commit to process safety. The organization really has to want to do it and to do it well. And then if we've got that commitment, we can do the rest. We can understand the hazards and risks. We can manage those risks. And of course, we will always need to learn from experience because we'll never get everything perfect. So within this pyramid, you can see at the bottom you have the leadership and the organization, all of the things that underpin the organization. But when it comes to the second layer, the model and methodology, this is where our process safety management system comes in. And we have a number of techniques that we can use for that understanding of hazards and risks, like bow tie, Swiss cheese, etc. So really, within any kind of process safety management framework, asset integrity is a very important element because we need to keep our facilities robust, reliable, all of those things that we've said over the entire life cycle. So there is really a very clear line of sight between your process safety management system, whichever framework you use, and the need for a strong and optimized asset integrity program. Thanks, Ron.
Just a quick question, Ron. We've had one question. Are we able to share the slide pack after this?
Absolutely.
Okay?
We'll share it as a PDF. No problem at all.
Fantastic. Thank you.
Okay. Andy, it's still yours.
Okay, and we have within our design, we have various barriers or layers of protection that are in place to keep us robust. So to keep us safe, to prevent the loss of containment. So we have our basic process control systems. We have our operator action based on alarms. We have our safety instrumented systems to bring us to a safe shutdown. And then we have active protections such as pressure release devices, in which case we are starting to get some partial loss of containment because we're discharging through the relief valve on the bursting disc. Then we have passive protection like bunding. We have our plant emergency response. And ultimately, we have our community emergency response. So what we're seeing here is both sides of the bow tie. And really what we want to do in order to ensure that we have a robust asset is to have the effective barriers on both sides of the bow tie. And when it comes to asset integrity, this is all about having, first of all, the facility designed well, but then really maintained over that life cycle to give us the protection that we need throughout the operating life cycle of the facility. So these are the different measures that we have in place to either prevent an incident or to mitigate the consequences.
All right, thanks, Andy. Right, so we've set the scene. Now, what API and ASME are helping us is API and ASME, they have published a number of codes, a number of recommended practices, a number of bulletins, and specifically, when we're talking integrity, API has released the Bulletin 1178 and several recommended practices just for pipeline. And also for offshore, we've got a number of publications. Because one of the reasons why API does publish some of these recommended practices and bulletins is that we have had incidents in the past. And as we see that we have incidents, every time an incident does occur, there's an investigation. We try and figure out what's gone wrong. Now, what API has done is they've given us a complete suite of recommended practices and standards, as well as these specific pipeline and offshore publications. And if we're talking about layers of protection, such as Andy mentioned in the last slide, if we go over to the right-hand side here, right in the middle of this, when we first start and we build our plant, we're going to build our plant to a recognized construction code. So usually in the oil and gas business, we're talking ASME. So B31 for piping, boiler and pressure vessel code for pressure vessels, and so on. And around that, we've got a number of extra layers of protection. And certainly as far as the equipment's concerned, what we're going to do is we're going to say, well, what could actually go wrong? So we need to be able to identify what the damage mechanisms are. Now, API's helped us with that. They've got a nice publication, API 571. And if anyone is involved in equipment integrity or inspections, you really should have a copy of API 571. It is very, very useful. Now, once you know what could go wrong, you can say, well, how can I identify what this thing is before it becomes a problem, before it becomes a loss of containment? And that usually means we're going to do some inspections. And the inspection codes within API, 510 for pressure vessels, 570 for piping, 653 for atmospheric storage tanks. Now, once we got our inspection code, we know what types of inspections to do. We then say, well, how can I organize these inspections? And probably the favorite way of doing this is with risk-based inspection. And with API, that's going to be API 580. 580 is, I call that a philosophy document. With API 580, we've got a document that tells us what risk-based inspection is. And API 581, it's a step-by-step procedure on how to implement RBI. So now we know what possibly could go wrong. We know what inspections we should be doing. We've organized these inspections into a risk-based inspection program. Occasionally, you're going to come across some problems which are quite serious. And you might have a problem, let's say, for example, the examiner has looked at a pressure vessel and they see that there's some severe corrosion at the oil-water interface. So some very heavy pitting. And that pitting has gone so deep, it's gone below the minimum allowed thickness for that pressure vessel. And you've got a question to answer. Do I have to shut this thing down right now? Or can I keep it in service until we can take the vessel out of service at a time that suits me, that suits the company? Now, this is where fitness for service comes in. So when you're doing fitness for service, you can evaluate the strength of that piece of equipment. Is it strong enough to avoid a loss of containment? And there is a joint standard between API and ASME. So API 579-1/ASME FFS-1. That is a standard. All right. What I'd like to do now is to look at some specifics. And we're going to talk about why these things happen. So all those things that we just mentioned, we talked about what are the damage mechanisms potentially. Well, let's have a look. API 571 is one of our best publications. It's a list of damage mechanisms that affect equipment in the oil and gas industry. Now, don't be misled by the title of API 571, because it does say it's for equipment in the downstream or refining industry. These damage mechanisms affect equipment in all aspects of the oil and gas industry. And API 571 divides the damage mechanism types into wall thinning and pitting, stress-driven damage, cracking and fracture, physical deformation, and metallurgical environmental damage. Now, I'm going to dive into each one of those. And first of all, wall thinning and pitting. Several types. If we start off with the basics, galvanic corrosion, chemical corrosion, dissimilar metals, and so on. But look at this one, CUI. Yep.
So we do have a question, Ron. We do have a question. And this is from Jesus Alberto. Excuse me if I've pronounced that incorrectly. The question is, in case of loss of material above 80%, which is the best standard to be used for FFS
Okay, all right. The standard for the oil and gas business is API 579. Well, API 579/ASME FFS. Within that standard, there are a number of different parts which address different types of damage mechanisms. If you're talking about material loss above 80%, you're probably talking about general metal loss. Well, it could be general metal loss or it could be local metal loss. Now, once you do get into that, the standard is it's a 3-level approach to identify, well, first of all, is this thing strong enough to put back in service? So, say for example, this is general metal loss. What you would do is you take a grid of wall thickness, and then you calculate the average across a certain area, and there are rules within the standard about how big an area that should be. So it's not just any old average. And then what we do, you look at the strength of the material, you calculate the minimum allowable wall thickness, you calculate the remaining strength factor, and then from that would tell you whether this piece of equipment is safe to put back in service or not. Now, a level 1 assessment is very conservative, but it's quite quick, it's quite easy to do. But if your equipment does not pass a level 1, you can go to a level 2. Now, a level 2 usually involves more calculations. And in the case of general metal loss, that usually involves some sort of graphic representation. So there would be a critical thickness profile that you'd have to develop. So it takes a bit longer. If it still fails a level 2, really what you then really need to do is to do a really deep analysis of the material. So in that case, you're probably going to be making a model, and you're probably looking at strength in very, very small areas. So that takes a lot of effort. And I normally recommend that most people here should be able to do a level 1 or a level 2. You really need a specialist to do a level 3. So I'm sorry, that's a long answer to a short question, but the question itself is quite complex.
It's a very good question, because if we look at historical incidents, this assessment of fitness for service is often something that we get wrong. One classic example, go to the Chemical Safety Board and look at the Chevron Richmond refinery incident.
Yeah.
There was a decision taken in that particular case to keep on operating, even though the metal loss was very drastic in that particular case. So it's important that when we get these kind of findings, that as part of our MOC, we have the right kind of fitness for service assessment, and we're making risk-based judgments on whether we can continue in service.
Yeah.
I think to add to that as well, Andy, that particular case at Richmond, the inspection team had actually identified the thinning a number of years beforehand, yet there were similar failings on sister refineries, and then also ultimately it was a management decision based on a subjective opinion to decide that it was fit for service. So that's the quite worrying thing, where the actual study based on the standards and recommendations and codes were ignored ultimately.
Yeah.
I see we have a hand raised as well from...
That's Jesus. Does that answer your question, Jesus?
Yeah, no, I think thank you very much for the clarification. And I just want to refer a case we have recently in company. So we were doing a MFL in a pipe, let's say, coming from offshore to onshore.
Okay.
And the section onshore, part of it is below a swamp, okay, for which we can no access to do direct measurement. So the MFL identify 80% material loss. We run a second MFL. It was identifying the same. Okay, but the problem is that the contractors do not commit to any wall thickness remaining above 80%, and also ASME, let's say, recommend directly to repair Nevertheless, the API 579, okay, allow you to go, okay, for this level 1 or 2 assessment. Yeah. But again, so it was not easy to really convince, on this situation where you can have access to measure directly, okay, to continue with the level 1 and level 2 assessment,
Yep.
And I mean, the situation here, we just, at the end, the risk was assessed. The pipeline was stopped for a while. We went with a UT robot. We could get to the point, and still the robot indicated that it is lamination. Yeah. So, so it's still not clear. Yeah. But this is because it raises a question that this case above 80%, we were recommended strongly to stop. Nevertheless, the pipeline was derated. It was initially rated for 80 bar, but we were working about 5 bars at this point, so quite derated. And so here we mainly assume the risk. We continue, and we try to get to repair, but it's still a little bit diffused information, even if the UT indicated lamination.
All right, and you used the magic word there, and that was the risk. And all of these things, all of these standards, they do give you these guidelines, and they do give you a pass-fail rule set. But at the end of the day, if you look at the introduction to any of these standards or any of these codes, it always says, this is a guide and the decision is yours. And so you always have to decide, what is the worst case? What could happen? And if the worst case is acceptable, you can go with it, but it's your signature at the end of the day. And if you get a loss of containment, particularly if it's an offshore pipeline, and I take it this is an oil pipeline?
Yes, it is.
Yeah, because if you get an oil pipeline, if you get a spill in an oil pipeline, then governments get involved and it gets all sorts of problems. But by identifying the risk, knowing the strength, and you did a derate, which is a sensible thing to do, so it lowered the pressure, and it gives you time to actually do a repair or a replacement. So I can't say yes or no. It's always complicated.
Yeah. Thank you very much.
We have another hand raised, Rob, from Malik.
Yes, afternoon. It was just his comment. Just his comment. I just thought to at least share my thoughts on that one, because generally speaking, most pipeline fitness for service code will limit your assessment, the code applicability to 85%. DNV, for instance, does that. F101 as me up until last revision was actually 80% limit for the code applicability. It just means that all the testing, all the validation they've done is validated to that limit. Anything above 80% means you need to actually verify the thickness you're reporting. It's not, hence the limit of the code itself. They're saying what's left of the thickness of that pipeline. It's when you factor in the fact that of the tolerance of the tools you're using, like MFL, you mentioned, Jesus. MFL has a tolerance ranging up to 20% in some cases, depending on where the defects are. They're just saying you're in a region where, although they're reporting 80%, in actual fact, it might be a lot higher than 80%. So you want to verify that thickness before you do your assessment, hence the limit of the code. Yeah, so that's the issue we're facing. It's not so much the applicability of the formula itself. If you have a means of confirming for sure that it is 80% left, then yeah, you can go ahead and do your calculation on that basis. So that's essentially what the concerns are when it comes to things like that.
Yeah, good point, Malik. You're absolutely correct. And it's none of these techniques that we're using for measurements are perfect. And 20% accuracy, you think, wow, that seems okay. But when you're down to 80%, I mean, that could add up to 100% quite easily. But if you can verify and you know what it is, then you can use the fitness for service. Okay. I do want to crack on because we do have a lot to get through here. I did mention on here, back to this screen, the wall thinning and pitting, galvanic and chemical corrosion, CUI, corrosion under insulation, is a big, big issue all around the world. So it's definitely something to look for. Erosion, high fluid velocities. In fact, we just developed a new training material for erosion, mainly because when you're working with flow lines and you're trying to determine what the erosional velocity should be, we tend to use API 14E. And what we've found is that API 14E is not the most accurate way of determining an erosional velocity. So what we've done is we've put a lot of effort into putting an online learning module together to help people to figure that out. In fact, I think that's just been released last week. We also got mechanical damage. Well, if anyone's ever been involved with digging up a pipeline onshore, you know that's you really want to be careful where those diggers are. And if you're not sure, it's hand dig, and that's painful. MIC, microbiological induced wall thinning. And I think the classic case for that is in Alaska in 2005, when there was MIC in the Trans-Alaska Pipeline. And I think BP lost over $1 billion because of that. Now, that was one type of damage mechanisms, a grouping of damage mechanisms. Another group is stress-driven damage, stress rupture, that's overpressure or so on. Fatigue. It's a big issue. And in the recent versions of API 579, there's now quite a comprehensive section on fatigue analysis. We talk about things like hanging big things off little things. What we're talking about there is if you've got let's say you've got a drain line, so maybe it's a 1-inch or a 2-inch drain line. Don't put a big heavy valve on the end of that could swing around, because any sort of vibration, any movement will cause high stresses in that small drain line and could eventually cause a fatigue crack. And then you've got these issues with creep and strain aging. And one thing to think about with this, a lot of our plants are quite old. And that means as they get old, and particularly if they're under high stress and maybe high temperatures, then the metallurgy of the steel can change. And there have been a lot of instances where old steel has failed when new steel would not. Physical deformation. This is an example. A friend of mine sent me this photograph. This was a pressure vessel that was in a post-well heat treat oven. And you can see that there was a pretty catastrophic collapse. But the things that we're talking about here is manufacturing errors, construction errors, material problems. Things can be damaged in transit. It happens. I've seen vessels dropped from cranes. Metallurgy changes. Fire damage. Fire damage can take, it can take two forms. You can have direct flame impingement, so the metal stays very hot for a long time. In effect, the metal then could become very soft, maybe a little bit too ductile. Then along comes the fire department and they sprays it with cold water. So now you get hardening. So you get a lot of martensite formation, and you can end up with very hard material that could become brittle and can crack quite easily.
Ron,
And then,
we have a question, and it's the question is from Kenneth Allen regarding what's the cause of the collapse of that vessel. It's basically it's not a Yorkshire pudding effect, where the oven's being opened too quickly and the pastry's sagged. But I'll let you explain, even though we know, yeah.
It's quite difficult to see, but inside here, there's a lot of structural steel, basically scaffolding poles. And these were meant to support the vessel when it was in the oven. and unfortunately the structure inside was not put in properly. It wasn't strong enough. At least that's what I was told. I wasn't on site when this happened, but I was told that the weight of the steel when it's got hot, the weight of the steel bore down on the scaffolding poles, and the scaffolding poles gave way. Then the whole thing collapsed. Unusual one, but it happened.
Thanks.
You're very welcome. I hope it doesn't happen to you. Okay, the other one, environment-assisted cracking. I think we're all familiar with chloride stress corrosion cracking. We got all different types in refining. Refining specific. There are other mechanisms like high temperature hydrogen attack, titanium hydriding. Titanium hydriding, to be honest, I've never come across that. I've never actually had that, but HTEHA, I have. And then you've got high temperature corrosion. Okay, so I saw a question there. Can you relate to facilities management?
Thanks, Ron.
Okay. Yeah. All right. All of these problems, it depends on your definition of that word facilities. Because we're an American-based company, when we talk facilities and we talk facilities engineering, we are talking about production and process equipment. And all of these damage mechanisms that I've been talking about are or can be related to process equipment. So it's related to facilities management. If you're in the UK, facilities management tends to be buildings. And some of these damage mechanisms can occur. I can give you, for instance, I was doing some consultancy at a factory in the UK that it was a food factory. I won't say who it was, but as I was walking through the plant, there was the ceiling was about 4 meters high, and there was a maze of stainless steel pipework. And as I was walking around with the chief engineer, there was a crack, a bang, and a thud, and a flange broke on one of these sections of pipe. So this is something like a 4-inch pipe. And the pipe's hanging down, and all of this food stuff came flowing and glugging out of the pipe, and it collected on the floor. And alarms were going off all over the place. And the chief engineer did what all chief engineers do and started telling everyone what to do. 3 of his guys ran up, shut everything down. They got the piece of pipe down and a new piece of pipe up in place. And I was standing there watching this. In less than 20 minutes, they had a new section of pipe up in place. And the plant went back into service. Anyway, we went back to the chief engineer's office. And as we sat there, I just mentioned I was very impressed with his production people, or the maintenance guys, to get the section of pipe up in about 15, 20 minutes. And his response was, no, it happens all the time. As we get 2 or 3 of them a week. I said, really? And we started chatting, and he said something you should never say to a consultant. And he said, oh, we make loads of money. And I thought, well, okay, I can help you with that. But then he said, you know, the biggest part of our process, the biggest constituent of what we make is salt water. And something went click in my mind. And I said, well, what is the pipe material? And he said, oh, it's 316L, stainless steel. I said, I think I know what your problem is. And what we did was I opened my laptop and we pulled up a copy of API 571, and it was chloride stress corrosion cracking. If you've got chlorides in an austenitic stainless steel you will get cracking. Now, all of the pipe work in this plant was 316L. And it meant that the people who designed that plant did not understand what was going on. They did not understand that match of the process and the chemistry of the steel. And that was a big plant. So can I relate this to asset integrity, to facilities management? Understand your equipment, understand your process, understand the materials. Okay, I want to carry on because time is getting on and I think we're having just too much fun, guys. I want to ask you guys a question now. Again, we're going to do Slido. According to API, what is the most common specific damage mechanism affecting the oil and gas industry worldwide? Go on, see if you can come up with this answer. Get your cell phones out.
We have 10 votes in so far. You got it up on the screen.
Okay. I'll just give it a minute. Oh, I can see it's coming up there. We've got 12, 14, 15. All right,
Just waiting
16.
for 44 more.
I'm not so sure I can wait all that time because I think we might run out of time if we're not careful.
Yeah.
All right, we've got 23, 25, 26, 28. Right, guys, I'm gonna dive on now. Let's see what we think. Well done. Well done. According to API, CUI, corrosion under insulation, accounts for 60% of all corrosion issues. So be careful of CUI.
We've got a few more questions come up, Ron.
Yeah.
Well, there's a comment, understand changes to process over life cycle. That's a really good comment. And
it is,
it is
a good comment.
Change is, seriously linked to that. So change management, we've all witnessed poor implementation of that. There's another question. What material did you recommend for the CSCC issue?
Oh, that was actually funny. When I mentioned it to the chief engineer, his face went grey, and he said, "What do you mean? I'm going to change all my steel in the pipe in the factory?" I said, "Well, yeah, really." And he said, "Nah." He says, "They're going to shut us down in 2 years. We're just going to live with it." So they just kept it, and they just kept. As far as I know, I mean, that was 15 years ago. The plant is still operating, and they're changing pipe 2 or 3 times a week. So if you want a good job, start selling pipe in Liverpool.
We do have another comment. Somebody thought it wasn't fair. General corrosion covers corrosion under insulation.
General corrosion covers CUI. Well, I think we could argue about points on that one. All right. Anyway.
Thank you for that.
All right. Let's run on. Inspection management, in the mitigations, because what we've done is we've said, look, these are the things that could go wrong. What we want to do now is to say, well, how can I stop it going wrong? Well, certainly we need to manage our inspections, and that means you need to monitor. You need to look at your chemistry, look at your corrosion mechanisms, understand the corrosion loops, pigging, if necessary, over piping. You've got to understand how to do the appropriate repairs. And that means you've got to have strategies, process management, operations management, and information validation. I've gone to many, many plants where we don't actually know what the material of the steel is. And that could be problematic. Okay. Now, I'm just going to run through this really quick. If you've got damage mechanisms, or you expect damage mechanisms, which are going to be visible at the surface, and that could apply to corrosion, erosion, mechanical damage, structural problems, VT would work. And that could be borescope, fiberscope, and so on. It's quick, it's accurate. The downside is surface defects only. Now, if you want to identify a subsurface defect, and particularly in welds, then you might want to use RT. Now, RT is, again, dimensionally accurate, and it does give you 100% penetration. So that's good. The downside is if you are doing any RT, then you have to rope off that area because it's relatively dangerous, because we're talking about radiation. It takes time and it takes expertise. And we say the very specific interpretation of images. Some of these images are not the easiest to interpret. So you need someone who understands what's actually going on.
Can
Now,
I
if you
just
don't
add
want
a
to do-
comment to that? Son,
Yeah, sure.
Whilst you're on the radiographic testing. Also, don't forget to consider any nucleonic measurement devices around the area. You know, there's
good point.
one of the cons is having an unplanned shutdown of a unit because of the signal from the radiographic testing. I know, I've witnessed it.
There are always downsides. If you decide to go with
Is anyone
UT,
using that pulse system yet? Pulsed X-rays that don't affect the nucleonics. Anyone using?
I haven't. Is anyone
No.
here?
Something
Or have
to
you
consider.
you just read about it, Andy?
Well, we've had the information passed on by contractors that it's currently being used elsewhere and to be considered. But it doesn't affect your nucleonics because it pulses micro pulses of radiation that the nucleonics don't pick up.
Cool.
Good
I've
to
not come
know.
across that.
Thanks for sharing, Andy.
Anyway, on UT, we got pulse echo. Pulse echoes are mainly for wall thickness checks. I've got phased array or time of flight. And the two pictures I've got there are actually my two grandsons when they were in the womb. And yes, that was my grandson. That was taken with phased array. And this is taken with time of flight. The time of flight is more accurate, but it's much, much more expensive. Or you could use MT. MT, particularly if you're talking of magnetic particle. If you're checking a weld, like a root weld, and you've got to get in and check it for cracks or any inclusions, but you've only got a limited amount of time. So you've got to do it before it cools down too quickly. So MT is perfect for this. We've got different types. I mean, we've already mentioned MFL, and MFL is very useful, but it is something of an approximation. Now then, so what we've done, we've said we know what loss of containment is. We've said we know what could go wrong, why we get loss of containment. What we then say is, well, we now know how we can identify those damage mechanisms before they cause loss of containment. And it may well be you don't just use one type of technology, you might use several, particularly if it's a high risk area. And Andy, I'm going to ask you, can you jump in on this one? Tell us about risk.
Yeah, this is very much a standard risk matrix that everyone will know and love, and we're always looking at what is the probability or the likelihood of a particular incident, and we're looking at what would be the consequence, and then based on that assessment, we determine what action we need to take. So if we're in the green area, we're good. If we're in as this diagram shows, the yellow or the orange area, we're into the ALARP region where we need to be able to demonstrate ALARP. And clearly, if we're in the red region, we've got an acceptable risk. So if we are assessing our risk and determining our inspection based on that, then we need to understand where we are in the matrix and then what action are we going to take.
Yeah,
And
this
this,
just yeah, go ahead, Andy.
yeah, this is very much a standard risk matrix. It's typical of what is used by many organizations. Sometimes you might see a 5x5. I've seen as broad as an 8x8, but the general principle is the same. And we really want to reduce the risk to as low a level as practically possible. So there is this concept of a LARP in the middle, and that concept of a LARP, it came originally from the mining industry in the UK, where a mine worker was killed, and his lawyers from his family argued that the whole of the mine should have been shuttered. All of the seams should have been shuttered to prevent any collapse killing someone. And the court said, no, that is not reasonably practicable. It'd be too expensive, and the amount of risk it would be reducing is too low. And that really developed this concept of a LARP. So we have the intolerable region where we can't accept the risk. That's at the top of the pyramid here. We have the broadly acceptable region at the bottom. And in the middle, that region is tolerable only if that further risk reduction is either not practical or the cost is disproportionate to the benefit, with the background being that it came from that mining incident. And every organization will have a different set of criteria for what is determined as acceptable risk.
Okay, thanks, Andy. I just want to put this one up because sometimes people wonder, how can I actually determine how can I quantify what that risk is? API 581 does give you some guidance on that. And the example here is in this area, we're talking about financial consequence. And what API says, if your financial loss is less than $10,000, it's a category A. If it's more than 10 million, it's a category E, and so on. Now we put all this together, and what we should end up with is an RBI plan. Now what this plan is doing, it's saying, let's just figure out what could go wrong. Let's determine what's the most appropriate type of technology to detect it. Let's figure out how often we should take the readings, and what you end up with is an inspection plan. And what we're trying to do is concentrate our effort where the risk is highest. So if you identify that a loss of containment is probable, and again, we'll quantify that, and if the consequences are severe, and again, we can quantify that, we can place that risk on that risk matrix. Now, if I've got two pieces of equipment, let's say I've got a header that's got a lot of H2S gas in, and I've got a potable water tank, I think about the consequences. I'm going to spend more time looking at that H2S header than the potable water tank, because the potable water tank doesn't usually kill people. Yep.
Just to let you know, we've got 5 minutes remaining of the meeting time.
Yeah, we're just finishing up now.
Yep.
So basically the RBI, you set up an RBI team, and the RBI team should be headed up by inspectors and examiners. They would be full-time. Not everyone needs to be full-time. You might have an operator who understands this part of the plant very, very well. Well, the operator would only be in the RBI team when you're assessing that area. You group your components into inspectable units. So that would depend on where the shutdown valves are. If I take this pressure vessel out, that piece of piping also has to come out. So let's do all that together. Prioritize the risks associated with each equipment, develop the plan, carry out the inspections, analyze the results. And basically what we're looking for here is, am I seeing what I expected? If we see that it is as we expect, all right, we just go back and we do it again. If we find that the rate of degradation was not what we expected, or we see a different type of damage, that means that my initial RBI assessment was not perfectly correct. The point of this is that the RBI plan is a living document. You do not do an RBI assessment and say, I'm done. It doesn't work that way. And what you should end up with is a document for each piece of equipment or each inspectable unit that tells you what it is, tag number, serial number, and so on. We've got a schematic of what it does, showing where nozzles are and so on. We've got a service brief. We've got what materials are involved and what the corrosion risk is and what the failure risk is. And then we've got a comment down here to say, how am I actually going to do this inspection? So what we've done, we've identified the problems. We've identified the appropriate inspections. We've identified and calculated the risk associated with that loss of containment with our inspections. We've put that all together into an inspection plan. So I'm going to ask you guys again, using Slido, using one word, what do you think is the greatest threat to a successful integrity management implementation? I tell you, there's no right answer to this because there are many. Inspections themselves and cost. Oh, dollars raise their heads yet again. Proper inspection with reliable data, oh, evergreen. Yeah. Inconsistency. Management. I've got two different managements there. Operations. Appreciation of the failures, so it's understanding. Normalization, that's a big one. If we tend to think, oh yeah, it's always been like this, so it's not going to be a problem. No, that's where the worst disasters happen.
That's what drove the requirement for the process safety cultural change program, Andy, isn't it?
Yep.
It is.
Silos. Oh yeah.
Yeah.
People, I just live in my little world, and all I'm interested in is my little world. Forget about what's happening. What I do is surely that's not going to affect anyone else downstream. Well, yes, it will, huh?
And the appreciation of failures, that's a great one as well. And like I mentioned before, we deliver a process safety cultural change program, and we present case studies, and they can see the failures, what can happen when, implementation of recommendations isn't fulfilled. So we use the Chemical Safety Board videos on a few instances. So senior management can get an appreciation of what can happen.
Yeah. Okay, guys, I'm going to dive on.
Definitely.
Very, very good. Now, I'm going to introduce you to something else now. What should I avoid? And I'm not saying that this is 100% accurate, and I'm not going to go through all of this. You'll see this when you get the slide pack. But essentially, what this is doing, it's mirroring what you've just said. The issue here is, what makes it really interesting, is that we know what the problems are. We know that you need management buy-in. We know that you need consistency. We know that we need this good understanding. We know we need a good risk assessment methodology. So there's no silver bullet here. There's no magic formula. It's be consistent, be methodical, and you'll work safely.
And I think as well, Ron, learn from experience. If we get any incidents that indicate we've had any of these issues, then we need to capture that through the incident investigation process and put an effective corrective action in place to resolve it.
Yeah, very good. So just to wrap up, figure out what the physical roots of the equipment integrity deterioration could be. Identify what you can do to maintain asset integrity, and we say inspect, 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 and then do a repair. Don't just say it'll be fine. Management, can I run this for another 6 months? No. Get this thing out now. And if you need management buy-in to say yes, if we've identified there's a problem, we need to get it fixed. That's the only way you're going to avoid this loss of containment. How do I decide on which inspection technologies to use? Well, understand that some things work better in some areas than others. Some inspection technologies are better than others for specific defects. And it might be you need more than one technology. And Andy, I'm going to just pass this on to you now, just to wrap us up.
Thank you, Ron. Yeah, just for those who don't necessarily know us, Petroskills has been around for a long time as an organization that is there to help people improve in the oil and gas space. We have a range of training resources, from face-to-face training through virtual training and into digital learning. And in short, if there's anything that has promoted any interest from today, or you've got any questions in general, then please feel free to reach out to any of us. I've put our contact details in the chat. We'd be delighted to help. And at the heart of all that we do as Petroskills, we have this Petroskills Alliance, which has been in place for coming up to 25 years now. And it's an alliance of many of the major players worldwide. And that means that all of our content is based off competency maps, which are reviewed, approved by our alliance members, so that we are making sure that what we do provide is based on industry best practice. It's based on industry standards, which gives us I think, a good seal of approval in terms of the quality of what we can deliver.
And that's us. So if any, I know we've run over a few minutes, but we started a few minutes late. So I think we're just on the hour. So if anyone has any other questions, now's the time. Or you could actually send us an email later if you wanted to.
I have a question, Ron. Are you going to share the slide deck on the chat here?
I probably could do. I won't have to come out. I'll have to close this down. I'll stop sharing.
Super.
Thank you for that feedback. Much appreciated.
Thank you, gents, for the feedback. And yeah, I think our colleague Ron is going to be dropping that link for the slide deck into the chat. So if you wanted to just hang on so you can grab a copy, it'd be fantastic.
I'll try to be fair, I'm not absolutely certain we can do this. I might have to do it through the university.
Yeah, everyone registered for the webinar, so we will do a follow-up via the registration.
Superb.
Thank you very much.
Thank you, gents.
Cheers.
Thank you. Yeah, I think that's best. It's not allowing me to share. So we'll send it out on an email. Yeah.
Excellent.
And I'm now going to stop recording.